were the leading expert about plasma physics, and in particular also like pulsar magnetosphere. So I also want to say just in the beginning that after the break, we will have also two more like particle physics action-oriented talk by Sam Whitty and Josh Foster, again about magnetospheres. So I think that this interplay is very nice, and I also thanks Jens and other people from from the group of Sasha to join us. So please, Sasha, the stage is yours, and have fun.
Thank you. Yeah, this talk is oriented just to give an introduction of what we think about this astrophysical objects called neutron stars. I'm not going to say anything about how they produce axions, but this will probably be covered in next sections. So just to give everyone on the same stage, these pulsars are rotating neutron stars, very small 12-kilometer size objects which rotate very quickly. They're equipped with very strong magnetic fields. Typical pulsar would have a magnetic field of 10 to 12 Gauss, and the most extreme cases would go all the way to 10 to 14 and 10 to 15. More or less, all of the fascinating physics that comes outside comes from the rotational energy of the spinning magnet. So you basically have a very highly conducting sphere which rotates around its axis at ridiculous speed. The periods of the stars go from a few milliseconds to a few seconds. And then if you have 10 to 12 Gauss field, you have a rotation. There is a very simple phenomenon called unipolar induction. You basically start to induce voltage on the surface of this neutron star. So this experiment with a battery is some sort of pulsar in reverse. Here you have a magnet and a battery, and you have a wire that connects them, and the wire starts spinning because there is a current running through this wire because of the battery. And then, since there is a magnetic field coming from this magnet, there is a torque of the Lorentz force, which starts spinning the wire. So pulsar is a bit in reverse. You have the magnet and you have rotation. So this generates voltage. So pulsar is like a battery in this sense. It produces voltage across the surface of the neutron star. So what happens is that part of this voltage points along the magnetic field lines, which are sticking out of the neutron star surface. So now you have electric field, which is very strong. And since the upper layers of this neutron stars are like some sort of normal matter, this is like a gaseous type atmosphere with hydrogen and potentially heavier elements and electrons, of course. This can be really easily pulled out from this atmosphere by the electric field. So if you're in a vacuum and you just have a spinning magnet, the surroundings will quickly start to be populated by electrons and ions, just because there are these electric fields which pull out charges from the atmosphere. Electrons that get accelerated along the magnetic field lines, that they accelerate to high energies, they quickly go to Lorentz factors of 10 to 6, 10 to 7. If nothing would happen further out, electron would have an energy of Lorentz factor of 10 to the 10. This doesn't happen though, because as they reach the energy of 10 to 6 or 10 to 7, these particles start to radiate GeV photons just because they travel in curved magnetic field lines. They're accelerating to a local center of curvature, and this is why they're emitting photons. This is what we call curvature photons. And the GeV photon propagating across magnetic field lines is easily converted into electron-positron pair in the 10 to 12 Gauss magnetic field. So basically, you see the charged particles from the atmosphere, they accelerate, they emit photons, you start producing electron-positron pairs. The pairs are then split by the electric field. Electrons go in one way, positrons go another way. They produce secondary photons. For example, they're born to a non-zero Landau level because just to satisfy energy and momentum conservation, some of these particles have a non-zero momentum across the field lines. All of this momentum is quickly irradiated at synchrotron radiation. The time to fall back to zero's Landau state is like 10 to minus 14 seconds. So basically in the much faster than any characteristic time scale, you go down to zero state and produce more photons that can contribute more to the pair production. This is what we call pair discharge, the process of accelerating particles, emitting photons, producing pairs through the QED processes, and screening the electric field. Because once these pairs are produced, they basically want to kill the electric field. If you put the electron-positron pair into the electric field, positron will go along the electric field, electron will go in the opposite direction. The electric field that these particles create would want to remove the electric field that you put there in the first place. So that's like the zero-solder plasma physics that you should remember when you're thinking about the spare discharges. Basically, it takes not much density of electrons and positrons to remove this electric field. So this is a cartoon model. How we observe the sources is across the whole electromagnetic spectrum. They've been discovered in radio emission. Radio emission is peculiar because it's so bright that if you try to assign like what the radio astronomers call brightness temperature, basically fitting a Rayleigh-Jeans spectrum to the observed emission and inferring the effective thermal temperature out of it, the answer would be pretty ridiculous. In some cases, you would get the brightness temperature of 10 to 38 Kelvin, which means that the emission that you observe is coherent. And by coherent, I basically mean that the emission of all particles is not summed up as their intensities, but you have to add up their individual electric fields, and then you can get an n-square effect, where n is the number of emitters, and the effective emission would be much brighter than you would assume from a thermal source. This is a long-standing problem known for 50 years. The key is basically to understand how this radio emission is produced. Recently, pulsars have been observed in gamma rays. Fermi basically discovered a large population of young pulsars and millisecond pulsars as very bright gamma ray sources. These gamma rays are produced somewhere outside of neutron star surface, because if they would be produced very close, they would all be absorbed.
Sasha, sorry to interrupt you. Just to make sure, like you're always like on the slide about what is a pulsar, right? Even if you're talking about gamma ray, just to make sure.
I just want to really talk about the introduction.
Okay,
because,
yeah,
you know,
good.
The millisecond pulsars and young pulsars are very bright gamma ray sources. They're produced not close to the star for a simple reason that if they would be produced close to the star, they would be attenuated by the strong magnetic field. They would be converted into pairs, and there would be a very sharp cutoff in the spectrum, the super exponential cutoff, which is not observed. So from this, we could constrain that these photons, the gamma ray photons that we observe, are produced somewhere at the periphery in the magnetosphere. And depending on the source, there is the whole zoology in terms of how this, what we call light curves are oriented. So the horizontal axis here is the pulsar phase. You basically see it once or twice per period, and then this picture repeats as the pulsar is spinning. So every other period, you would have the same picture. And the zoology represents itself into how the peaks are oriented across the electromagnetic spectrum. For example, in crab, all of the peaks are more or less aligned in phase, which points to the non-trivial conclusion that all of the emission might come from the same region somewhere in the outer magnetosphere. In other pulsars, let's say such as Vela, for example, the peaks are very different. The radio peak is very distinguished from the gamma ray peak and X-ray peak. So there are many regions in the magnetosphere where an interesting action is particle acceleration and photon emission is occurring. Finally, next slide. The zero-solder cartoon picture to describe the physics of the sources is what's called the force-free electrodynamics. You don't have to know anything about plasma physics to basically understand what's going on here. The key assumption is that the magnetic field is so large that you basically forget about what matter is doing. This is momentum equation of the plasma. This is basically just a Lorentz force, charge density times electric field, electric force, J cross B, Lorentz force. And then on the right-hand side, there would be many terms that would know what the plasma is doing in response to this electromagnetic field. So here I would just say that this electric field is so large that basically the left-hand side is much bigger than the right-hand side. I basically throw all of the density and pressure terms and zeroing them out. And then I'm adding this condition that I described in the beginning, that if there is a dense plasma, then the electric field along the magnetic field should be shorted out. The plasma will redistribute itself, polarize, and provide electric field, which would remove the vacuum electric field of the star. So from these two assumptions, turns out you can derive the current that the plasma is providing just as a function of electromagnetic fields, and there are spatial gradients. So it's basically a plasma physics without the plasma. The current is provided solely by the electromagnetic field. And this electric current is in a source in Maxwell's equations, which are outlined here. This is Ampere's law, this is Faraday's law. The Ampere's law has a source, which is the electric current, and you can basically put this on the computer and try to get the answer. So this is how the progress has been made in the field. For 30 years before this work, people even did not know what's the shape of the magnetosphere, what's the geometry of the magnetic field and the electric field outside of the pulsar. And with numerical simulations, we've been able to understand at least how the general shape should look like. So this is the case of what we call aligned rotator. So this is where magnetic axis and rotational axis are aligned. They're pointing in the z direction. The magnetic field initially was dipolar. So there is a dipole sitting out of the neutron star. And then in the simulation, you start spinning this object and see what happens. So what happens is that some of these field lines remain closed. So these field lines, they start on the star and go back to the star. The field lines which originate very close from the magnetic pole, they open up to infinity. They start on the star and then leave out to infinity. An interesting feature happens here. This is this vertical line. We call it a light cylinder. So this is basically a cylindrical radius at which, if the plasma would want to co-rotate with the star, basically rotate together with the pulsar, it would have to do it with the speed of light. So obviously beyond the surface, the plasma can no longer co-rotate with the star. So what happens is that these field lines open up and the plasma streams radially away from the pulsar along this open field lines. In the process of the screening the electric field that I told you in the beginning, plasma drives the current. So basically, since electrons and positons have to respond differently to the electric field because they go in opposite directions, the steady state sets up a current. And this current produces a magnetic field component out of the simulation plane. So this is what shown with the color. There is a current flowing along the field lines, and this is basically like a current wire. So if you have a wire, there is a magnetic field which is toroidal to the wire. It's like wraps around the wire. So in this geometry, it's basically pointing out of the simulation plane. And they have opposite signs in two different hemispheres. And in the middle here, the two opposite polarities of the field touch each other. So basically here you have the reversal of both the in-plane component of the magnetic field and out of the plane component of the magnetic field. This is what we call a current sheet. So basically you have two opposite polarities of the magnetic field. They're very close to each other. This means in the steady state, there has to be a very strong current that supports a jump of this magnetic field. And as we'll see later, if you include more physics, this layer is very time dependent. Output from the neutron star. Basically what happens is that you have this rotational energy, and then it gets lost in form of this electromagnetically dominated wind, which leaves out to the surrounding medium. And simulation allows you to predict how much power this electromagnetic wind carries, and from that you can predict how much the pulsar spins down, because this is just the amount of energy that is lost from the source. So to model it better and to actually understand how the particles are accelerated, you have to go a bit deeper, just for the reason that all of the physics of particle acceleration, which means the production of photons, has been lost on the previous slide. In the previous slide, I neglected all of the regions where the particles can be accelerated. I said that everywhere the electric field is zero, the electric field along the magnetic field. So this means the particles cannot be accelerated and they cannot emit photons. So to do a step further, you have to model the plasma consistently. And since this is what we call collisionless plasma, the mean free path to Coulomb collisions of individual charges is much larger than the size of this magnetosphere and even larger than the distance where this pulsar wind meets the ISM, which would be like what we call a termination shock. These particles never collide with each other, like by Coulomb collisions. How they interact is that they basically create this charges and currents together, and they create the electromagnetic field, then interacts with the charges. So this is what's called real plasma physics, the collective interaction of charges via the self-created electromagnetic field. How you can model this on a computer is what's called the particle and cell technique. Basically, you have a computational grid which is discretized. You have electromagnetic field components sitting on this grid, and you have individual charges which are like basically clouds of real particles. You obviously cannot simulate the number of particles in a real system. You're simulating clumps of these particles which would follow similar tracks in the phase space. And how this works is that you have a ensemble of particles on the grid. You can find out the currents and charges from these particles, solve Maxwell's equations. Then you can recompute the electromagnetic force acting on these particles. You can then push the particles again and again find the new currents and charges to recreate your electromagnetic field. So this happens every time step, and this is how the simulation is going. In terms of assumptions, there are no assumptions here. You're modeling all the scales appropriate in the problem. This obviously has its own downsides because the typical scales at which this plasma physics is occurring is on sort of centimeter or tens of centimeters in the magnetosphere. The size of the magnetosphere is 1,000 kilometers. So obviously you cannot model the exact same scales that exist in nature. You have to downscale the ratio and bring this ratio to smaller just to be able to fit it into a computer. To model these magnetospheres of compact objects, you have to model also how they produce photons, and typically they produce photons through synchrotron radiation. These are very highly energetic particles. They reach easily the Lorentz factors of thousands, and the frequency of this radiation is much higher than the frequency of their motion, which is resolved by the code. Practically, you don't resolve this radiation by your electromagnetic equations. However, fortunately, if you just know the acceleration of the particle, you can compute everything about emission. So this is basically a subgrid model. These particles emit high energy emission. You know how much energy this should carry, and you subtract this energy from the produced particle, which is known as the radiation reaction force. So all of this is taken care of, and then the photons that these particles emit propagate across the grid, and they can produce pairs via either absorption in the electromagnetic field or by colliding with the other photon. I'll just show a few results which come out from these models. Basically, the first model, which was originally postulated by Goldreich and Julian back in 70s, basically at that time they didn't understand the pair production has to operate. They just relied on particles from the surface of a neutron star. Yet the cartoon picture that they draw was more or less correct. However, if you literally take their assumptions and only allow particles to leave from the surface, the result is very different. Instead of this picture with open field lines, the charges flying away from the neutron star, the currents, etc., you get this very weird state when basically you have what we call a dome, like this cloud of electrons on top of a neutron star and the cloud of positrons in the equatorial plane. So these particles are trapped. They don't leave from the neutron star. And the key to this is basically the whole configuration becomes charged. There is a macroscopic charge that sits with this plasma and the neutron star, and the electrons that leave the surface are then repelled back by the central charge of the neutron star. There is a small caveat to this, which is this spiral modes that you see in the equatorial plane. This is an instability developing in this ion torus orbiting around the neutron star. This happens because this torus is rotating differentially. It doesn't exactly correlate with the neutron star. And if you learn something about the fluid mechanics, you know that any shear flow should be basically unstable to something like a Kelvin-Helmholtz instability. So this is an analog of Kelvin-Helmholtz instability, which happens in a plasma where there is just one sign of charge. You have just one cloud of ions rotating with a differential speed, and this basically starts to bleed itself with this outflows of ions. However, the current that these ions drive is very small, and if the current is small, it doesn't allow to modify the surrounding magnetic field, and basically the solution doesn't produce any outflow or any noticeable spin down compared to the torque that you would just get by emitting electromagnetic wave in vacuum. So we think that this is a state of pulsars where they get old beyond million years. The voltage, this accelerating potential close to the neutron star becomes small, and none of this physics that I talked in the beginning can no longer operate. You don't get pair production, you don't get photons, and basically you get into the state of a dead pulsar. How the active pulsar looks like is shown in this video. This is a solution to the inclined rotator, where you basically have this charges and photons. This is plotted in a frame which correlates with the pulsar. So in reality, you have a 60-degree inclined rotator. So the magnetic axis is spinning around the vertical axis of rotation at 60 degrees, but then you can plot it in a frame which moves together with this magnetic moment. And in that frame, you expect to see a steady state, and this is what happens. You see that the field lines, which are shown in white, are nearly stable, and then the plasma density, the picture of the plasma density, which is shown as a volume rendering, barely changes. So this is a steady state. You see the same sort of surface outside of the light cylinder, which is the current sheet, which was in the beginning just the equatorial plane for the aligned rotator. Now this is this tilted plane in the full 3D. And you also see this interesting oscillations in the close to the star, which is where the whole of pair production discharge is operating. So I'll get back to this physics later. You can see in a slice how this picture looks like. So this is a slice through this three-dimensional magnetosphere. And basically you see similar picture. You see field lines which are sort of closed back to the star. You see these field lines which are open out. There is the outflow of both electrons and positrons on the field lines with this interesting time dependence, which I'll come back later, as I said. And then there is this current sheet where magnetic reconnection occurs and basically converts magnetic field energy into particles and photons. Why this current sheet is interesting is because you think that this current sheet is what produces the observed gamma rays. What happens is basically as magnetic field lines touch each other, they start reconnecting, their topologies start changing. The field lines which were initially anti-parallel start to reconnect to each other. And then that process, magnetic field energy is released, it gets converted to accelerated particles, and the synchrotron cooling time in the systems is so small that basically all of this energy that magnetic field just gave to the particles get immediately converted into gamma rays. Simulations allow to predict the efficiencies of this emission. By efficiency, I mean how much of the outgoing electromagnetic wind gets converted into gamma rays. And we found something like from 1 to 20%, which is consistent with observations by Fermi. You can find out what does this depend on. This we find mainly depends on the inclination angle of the pulsar. And you can plot light curves. So by light curve, I mean actually this profile of gamma rays as the pulsar is rotating, and you would see the photons as the pulsar is spinning. And this is what's showing on the right panel. Basically, this movie shows the total emissivity of all particles in all directions, shown as the gray color. You see that it highlights this interesting surface, which is the current sheet. And then an observer that sits where you're sitting would see a light curve that is plotted in this window. So basically, you see a patch of this current sheet twice per orbit as the particles are streaming towards you. So this is a very highly relativistic particles. You only see emission where the particle basically flies towards you, and you see this emission from a distributed region across this current sheet, which happens to happen twice per orbit. So this is why pulsars have double peak emission in general. This is pretty general behavior. So these are actual Fermi light curves. You typically see either just two peaks or a peak with the what we call bridge emission, the emission in between the two peaks. And on the right, you see light curves extracted from the simulation. The top panel is the 30 degrees inclined pulsar. You see two peaks with the emission in between. And then if you incline more to 60 degrees, which is the bottom figure, you just see two narrow peaks and nothing in between. We now model spectra. There is very interesting physics about how particles are accelerated, how emission is produced, etc. So I'll not go into that, but instead go to, which is probably more interesting to people interested in axions, is how this electric field is actually sort of screened close to the surface of a neutron star. And the observational hint to it is the polar radio emission, which has been observed now for more than 50 years. The basic ingredient why it comes somewhere from the surface is the narrowness of the peaks. You basically see that the radio emission covers a very small patch throughout the whole rotation period of the pulsar. And moreover, this width of the peak mainly scales with the size of this open field line region, which we know how it scales with the pulsar period. So this points to some compact emission source somewhere close to the neutron star. And we also know this from how the linear polarization of this emission behaves. If you have questions, I can answer them, but otherwise I would just move on. How we now model this is to try to understand in details how this process of pair production happens right next to the neutron star. And in this simulation, I'm basically not modeling the whole magnetosphere of a neutron star, but just something that happens close to the source. Here, the neutron star is a plate, not a spherical surface, located at the left side of the simulation box at x equal to 0. I'm tilting or sort of shearing it out of the plane. So in 2D, I cannot properly rotate the surface, but I can shear it in and out of plane, which mimics rotation. It would basically have the same dynamics. You would have electric fields induced outside of this conductor, which is on the left side. You have magnetic field threading the conductor across it. So this is your magnetic field of the pulsar. And the shearing produces your electric field. It starts to extract particles. Particles start to radiate photons. Photons get converted into pairs. The whole machine starts to sort of operate. On the left panel, you see the plasma density, which is produced in the simulation. And what's interesting, it's produced in cycles. So basically, you have a cycle where you have a lot of pair production. You start to see increased density of the plasma, and then nothing happens for a while. So I already sort of alluded to the fact why this happens in the beginning, because once you start producing pairs, these pairs start to screen electric field. And once electric field is screened, the new particles that are pulled out from the neutron star surface, they can no longer accelerate because there is no this electric field that could accelerate them. So once this electric field is screened, you can no longer have any more pair production episodes. And this is what happens in this panel. This is the electric field along the magnetic field, basically the field component that picks up particles and accelerates to high energies. You see periods when you go from deep blue, which means strong electric field particle acceleration, to near zero, this green, yellow kind of colors, where the whole electric field is screened and nothing happens. So if you're interested in sort of how the electric field sort of near the neutron star behaves and how this can give rise to axion production, this is what you're interested in. You're interested in time-dependent dynamics of the electric field along the magnetic field. So what the simulations show is that this is very time-dependent. You see episodes of when there is an electric field, and it gets efficiently screened and you have nothing. What's interesting also about this is that there is not only this time-dependent screening of the electric field, but also the emission of the electromagnetic wave. So what happens here is that this is magnetic field out of plane minus the average magnetic field that is just produced by the current that is launched by this conducting plate. So every time you have a screening event, you see this wavy component of the magnetic field, which represent electromagnetic waves. So this is interesting in context of observed radiation. And basically, we started trying to understand what happens here. And basically, what happens here is that you have merely electrostatic waves, which just oscillate the electric field component along the magnetic field, but it happens at an angle with respect to the magnetic field. So you have a transverse curl of this electrostatic electric field. And since you have a curl, you give rise to magnetic field. And this is what produces your electromagnetic waves. Like on the right panels, you see pointing flux. So there is equal pointing flux basically escaping and going back towards the star from these waves that are produced by oscillating plasma in the electric field. You can go even deeper if you want to understand the spectrum and frequencies of this radiation. You have to go very far into one-dimensional simulations because you have to model large range of scales. And the middle panel basically shows you what happens with the electric field. You start with a very large, nearly vacuum electric field. You introduce plasma that gets produced by photons depleted into the magnetic field. And the electric field starts ringing as these particles get introduced into the system. And as the more particles are introduced, you start to get larger and larger frequencies of the radiation. So this is shown between top and bottom row. In the top row on the left, you see the density, which is equal to 15 of the fiducial densities. As the density gets larger in the bottom row, you start to see smaller scale oscillations in the electric field. This is like higher frequency structures in the emission. We think this mechanism is promising to explain the broad bandness of the emission, because you see pulsars all the way from 30, more or less 30 megahertz to now tens of gigahertz. And this would be basically plasma frequency, the characteristic frequency at which these waves are oscillating in the variety of densities available in this very non-homogeneous and time-dependent clouds of electron-positron pairs that gets produced close to the star. If you're interested in how long this nonlinear stage happens and what's the dynamics of this parallel electric field, Libby Tolman and the Institute of Advanced Study now led the basically a very theoretical one-dimensional toy model of trying to understand how exactly the screening happens. And the major conclusions of that is basically there is a very short initial stage when the screening occurs exponentially. So the electric field gets very quickly screened to small values where the electric field is no longer able to sort of return the particles that are freshly introduced into the spare discharge. And then this exponential stage is followed by a very slow linear damping of the electric field as the new density is introduced. So again, if you're interested in axions, you're interested in the very strong electric field, the maximum one. So this is what happened in this very short exponential stage, which happens basically shorter than the light crossing time across 10% of this polar region on a neutron star. So basically microseconds. So over a microsecond, you have a nearly vacuum electric field near the neutron star, but then it's basically damped and you don't get any further electric field. Andrea, can you tell me how I'm doing on time? So
I mean, we don't have a lot also because like we planned this half an hour of break. So I think you are doing great here. So, you know, how much do you need?
Maybe 10 minutes at most.
But 10 minutes is okay.
At this point, I can stop at any point because this is the second sort of other story about radio emission, which concerns this famous pulsar in the Crab Nebula, which has this interesting feature that basically the emission that you see across the whole spectrum is aligned in phase. So this means that more or less the same emission from gamma rays to radio frequencies come from the same place. And as I said in the beginning, the gamma rays have to come from somewhere at the periphery of the magnetosphere. We think they come from the current sheet outside of the light cylinder, which means that the radio emission, the main radio emission, also has to come from the same place. And what's interesting is that you not only see these two components which is aligned with gamma rays, but in total you see 7 components of this radio emission. And what is mentioned, what is labeled as PC in this picture is what observers call a precursor emission, which actually looks like the polar radio emission from every other pulsar. So there is something which, Crab is also emitting as all the other pulsars, but something which is very different from most of the population. And we think this is coming from the outer magnetosphere. It has very peculiar features. If you really time resolve this emission, you find out that the emission is not continuous, but it comes to you in some sort of flashes of microsecond duration. So this is intensity versus time. And then there is the time resolved spectrum in the bottom panel. So you basically see individual broadband shots of roughly few microsecond long emission. And then some of this you can resolve even further into nanosecond long shots. So you have ridiculously bright radio emission coming almost over 4 nanoseconds. And if you do a quick algebra, you'll understand that the product of observed frequency times duration is order of unity. You have gigahertz emission over a few nanosecond duration. So you basically see very few spikes of the electric field inside of this clump, and then you don't see nothing. And observers think that the whole emission in few components of the radio emission in the crab is basically composed of this nanosecond shots of radiation. If you calculate the instantaneous brightness over this 1 nanosecond, the brightness is very large. It will basically reach 1% of the total sort of energy loss by a neutron star in the form of this electromagnetic wind. So over 1 nanosecond, that can even compete with gamma rays as intensity it is. So what we think is the mechanism is basically this time-dependent current sheet outside of the light cylinder gets fragmented into what we call magnetic islands. Basically, this is no longer a laminar surface where there are 2 annihilating magnetic field lines, but the surface gets fragmented into basically strong regions of magnetic field. We call them magnetic islands or plasmoids, and then the regions where there is no magnetic field. If you just compute pointing flux, the electromagnetic emission that leaves out from the system, you see that the pointing flux leaves in a very localized waves. So what happens here, if you just have 2 sort of clumps of the magnetic field inside of the current sheet, you collide them against each other. And the product of this interaction is obviously a magnetosonic kind wave. So basically the wave that carries the propagation, the disturbance of the magnetic field out of this current sheet, and it propagates away in the form of this very localized spherical kind of waves. So if you calculate the observed sort of product of frequency times duration, you will find obviously a factor of few, because you basically have few oscillations as these 2 islands are merging within each other. And then you have a clumps of these nanoshots as you have bigger islands sort of colliding with each other and smaller ones being formed at the interface between the 2. So an interesting question is how this happens in 3D. The process that I showed on the left side is a 2-dimensional simulation. What happens in 3D, we don't really know because we cannot simulate large enough systems. However, the existing hints, which are shown on the right-hand side, which is the global 3D simulation and the cut through this 3D simulation, is basically shows similar physics. So you see individual sort of over densities of plasma and the magnetic field in this sort of loopy circles right here. So this is what we call islands in 2D. In 3D, these are like sort of chunks of the magnetic field, quasi sort of spherical tubes, which would then collide with each other and produce this emission. We don't yet know how the efficiency differs between 2D and 3D, but these are sort of ongoing questions to understand how this mechanism and the mechanism that I showed you earlier about producing radio emission from the polar cap discharge operates on higher dimensions. There is an interesting hint that I will just point to you, and I think close at this point. Just this year, NICER observed enhancement of X-ray emission coming together with the arrivals of this giant radio pulses from crab, which now sort of gets onto solid grounds that it's a lot more energy getting released during the emission of this giant pulse. And honestly, there is no other region in the magnetosphere rather than this current sheet where magnetic reconnection happens. It can release so much energy so easily. So I think this picture of giant pulses coming from the reconnection layer gets now onto solid grounds. So this is just the high order conclusions of what I now think about the science is basically with this simulations with full plasma physics calculations, which we're now trying to address long-standing questions of how the sources produce gamma rays, radio emission from first principles. And basically they point to that there are two regions in the magnetosphere where there is interesting time-dependent dynamics, which gives rise to particle acceleration and photon emission. And those are this polar cap discharge, where you have QED cascades, production of pairs and photons, which is accompanied, we think, by production of radio waves, and magnetic reconnection when the energy of the magnetic field in the magnetosphere gets converted into particles and photons. There are many more interesting questions about pulsars, which I did not touch on here. Is trying to sort of leave the fundamentals and connections with what most of you are interested in. Thank you, and thanks for your attention. Happy to take any questions you might have.
So thanks a lot, Sasha, for the very nice and inspiring talk. So question for Sasha from the audience. Otherwise, I will start as usual, but please don't be shy in the audience. So if there is any question, I will give you the ball. Yes, Sam, please.
Yeah, thank you for the very nice talk. I actually have two questions, Andrei, if it's not too annoying.
Yeah, go ahead. Don't worry.
I wanted to ask the first question in the context of the polar cap discharge. To what extent in the future are we going to be able to use radio observations to sort of reverse engineer or infer the plasma dynamics during the damping of the electric field?
Right. So the using observations in this context is a bit hard because radio emission, unlike gamma rays, doesn't just propagate. Doesn't taking care about the plasma. So what we think happens is that basically, as the emission is still coupled to the plasma, its characteristics change. So there is some sort of a radiative transfer problem of how this plasma interacts back with the radiation. And the main channel of interactions are refraction and sort of exchange of polarization. So the polarization of this emission changes as it propagates out. And moreover, the emission doesn't propagate on straight lines, it refracts because there are gradients in the plasma density. So an interesting question that could be reverse engineered, I think, is whether this refraction can actually take into account and to observe dependence of how broad these profiles are and how wide they are as a function of frequency. So as more sort of multi-frequency radio observations of many pulsars are available, we could be able to basically try to reverse engineer this refraction problem. The polarization problem is also interesting, and I worked a bit on that too. But basically, you can put the constraints on how much density you have in the magnetosphere by not overproducing this effects of how the emission couples with the plasma, because observations do point to some sort of moderate degree of this interaction. In terms of this microsecond type dynamics, there are interesting hints from the microstructure of this radiation. Basically, you see features at a few tens of microseconds, how this emission is changing. And I think this can reflect of this time-dependent dynamics in the screening and reigniting the polar discharge. But this is not, some sort of direct reverse engineering. We first to have understand how exactly this intermittent dynamics translates into the observed microstructure. But in terms of physical understanding, I think there are many hints, and there will be more hints coming forward.
Okay, thank you. My second question was actually related to the particle and cell simulations of the oblique rotators that you mentioned. I was wondering to what extent we understand the relative distribution of ions versus electrons and positrons, in particular with regard to net charge densities and boost factors within the spatial distribution of the magnetosphere.
Right, this is a great question. So I think we understand which field lines emit ions pretty well. So you basically have this clouds of ions in the closed field line region where you basically don't have an active polar discharge. So these are just ions extracted with mildly relativistic velocities and sitting as a remnant of this equatorial disk, as if you remember this Goldrake and Julian kind of solution with a dome and the disk and the equator. So this disk of the ions is sort of remnant. The remnant of this disk does exist in the full oblique pair simulations. The interesting regions where ions could get to high energies is in this separatrix region which bounds the open and closed field lines. So basically, to carry this current along the separatrix, you need to extract ions from the neutron star surface, and you do extract them. So there are not just the pairs produced on the discharge which carry this current, but roughly 10% of that current is carried by ions. And it's interesting that once a sort of ions along the separatrix propagate to the Y point and to the current sheet, they basically tap the full history of the particle energization in the magnetosphere. They travel over the most sort of active regions where the particle can actually tap the potential drop. And more interesting, these ions in the current sheet, they don't suffer synchrotron losses because the mass of the ion is so much larger that they basically don't emit. So I think the ions are actually the most energetic particles in the system. Not in terms of the Lorentz factors, but in terms of the total energy. And there are not many of them. Like roughly, I think for a line rotator, you get something like 10% of surface integrated Goldrake-Julian flux. If you probably know what the Goldrake-Julian density is. So roughly 10% of that is carried away by this energetic ions in the equatorial current sheet. What are the consequences? Hard to say. Long before there have been speculations about how the energetic ions affect the termination shock when the pulsar wind hits the interstellar medium. But in terms of sort of dynamics of the magnetosphere, I'm not sure this has any sort of interesting effect.
Okay, thank you. I appreciate that.
Any more question for Sasha? So I didn't see, and so I will ask actually. I have a couple, but I will be at the Institute in Flatiron in 10 days. So I will ask you just one question, because like you focus also a lot on the electric field and also on E dot B. Okay, but actually for the axion physics, and you will listen from Sam and Josh talk. We also care a lot about the B field only, because there are different ways. In one way, you can produce axion to this, due to this E dot B, and so these polar caps, etc., is very important. And then you also have B, the B field, right? Just only the B field. So regarding the B field, even if you didn't touch it during the talk, but then I take profit of your presence here. In your simulation or in your calculation, like, do you have any hint, for example, of turbulences in the B field of this, this kind of like dipolar model? And if yes, on which scales would you expect to have, turbulence in plasma to cause also turbulence in the B field?
Well, yeah, this is a good question. Basically, if you go to this slide, basically, if you take a very sort of hands-off approach and say, what is this radio emission? I would tell you that this is like sort of turbulence in the in the response of the electric and magnetic field on small scales to time-dependent dynamics. This, however, all lives on very small scales. The magnetic field at the surface is so strong that you cannot really perturb the field of the neutron star close to the surface. The only sort of addition to the magnetic field that you produce is the toroidal field of the current. So there is a large scale current being extracted from the neutron star surface. It creates toroidal magnetic field, but its amplitude is, much less than the dipolar field of the surface. So basically all of the turbulence or, time-dependent dynamics, I don't call it turbulence because, there is nothing like a Kolmogorov or Goldreich-Sridhar type cascade in the systems. This all lives on plasma scales, basically on plasma skin depths, because Larmor radius is irrelevant in this problem. The Larmor radius can be just taken to zero safely.
Right.
So this all lives on centimeter-like scales, and its amplitudes are very small after you're past this exponential stage of screening that I said. Mm-hmm. My global answer to this would be the sort of afterglow of turbulence is the radio emission that comes out, but there is no sort of large scale changes to the pulsar field of that distance.
Okay.
What happens later as this time-dependent outflow streams out for thousands of kilometers? It's an interesting question. The relevant sort of observational window is the solar wind, the wind that the sun blows out to large scales. And we know that to a certain degree, it's quite turbulent, though the turbulence might be produced also by convective motions of the sun, which you don't have for the neutron star. Neutron star is just, a solid crust, which doesn't really move beyond certain events. So I think on large distances, it could be plausible, but on these distances, you also don't care because the field gets too low. So I think for questions about what the B field is and what E parallel is, I think we have very strong hints, at least in these young sources where we do know how pair production operates.
Okay, perfect, Sasha. Thanks a lot. So if there are no other questions, I would pass to the other speaker. And if you're around at the break and after, we can have other discussion. So now we have Malte. Malte, are you there?